Okay, so here's what we were talking about last time. So there's this other method that you can use to solve a first-order system when the matrix is non-diagonalizable. Now, this does require knowing the Jordan form and the Jordan basis. And, again, that's, something that we can't always do analytically. But, again, MATLAB can, right? MATLAB can always find this for us. So if you know that information, the following works very conveniently. The big plus about this method is that it avoids that whole back-solving process that's very tedious. And again, when you have a process that's tedious, that means that there's just tremendous opportunities for oopses, right? So, risky, you might even say. Okay, so here's the alternative method. We go to define this, weird definition called a matrix exponential. We talked about this last time. It's motivated by the same definition that we made for complex exponentials. Right? We've all gotten fairly accustomed to complex exponentials. Doesn't seem super weird anymore. Maybe just a little weird. And this is really, again, not that weird if you really think about it. And it turns out that the algebra of matrix exponentials is surprisingly familiar. Not 100% familiar, but surprisingly familiar. Okay, nice punchline. Matrix exponentials solve these kinds of differential equations. Right? So, which is totally awesome. So the big question then reduces down to, okay, how do I evaluate matrix exponentials? I know matrix exponential times vector is the solution I'm looking for. What does that mean in terms of buttons on my calculator? Right? Okay. So here's where, again, last time, as we did, we're going to skip a bunch of details. There is this formula. Again, I'm not going to show you where that comes from. You're not responsible for it. And this tells us a couple of things. For one thing, if you have an eigenvector, there's how you evaluate the matrix exponential times that eigenvector. Here you go. Matrix exponential times eigenvector. Nice, simple, convenient little formula. Okay. Which, by the way, follows immediately from that big formula. And it's a nice exercise to think that through. The big idea here is that if V is an eigenvector, A minus lambda I times V is 0. A minus lambda I squared times V is 0. Right? All of these terms over here in the extended matrix exponential formula, they all disappear. And all you have is e to the lambda x times v. Just like that. So it's an easy consequence of that formula up there in case you forget the formula. Okay. But you're perfectly allowed just to memorize that formula right there. Okay. All right. So what about Jordan basis vectors? I mean, sort of the whole purpose of this exercise is to how do we deal with the non-diagonalizable case? Our Jordan basis is going to have some eigenvectors, sure, but it's going to have some not eigenvectors. How do we deal with those? A bunch of details that, when I have time in Math 216, I like to be able to go through. It's a nice exercise, but this is really kind of digging a little deeper than is really necessary. So this is all optional to prove this formula. But I think it's very nice to know this formula, that in the case of a Jordan basis vector, matrix exponential times Jordan basis vector follows this formula. So I encourage you to just memorize that formula. Good news, the coefficients in this formula you've already probably memorized. Let's think about those coefficients. 1, 1/2, etc. 1 over a factorial. Right? Those are just the Taylor coefficients. Easy to remember. Right? You get an extra factor of x. In each term, there's an x, then an x squared, etc., increasing powers of x. And then, again, as you go through the terms, which Jordan basis vector, you just always move back by 1. So if you're applying this to the ith Jordan basis vector, the first term, you have the ith Jordan basis vector. In the next term, you have the previous Jordan basis vector. In the next term, the one previous to that, etc. You just keep stepping back one at a time. Okay, so we applied this formula last time to this example. You may recall this example we worked out through back solving, and it was quite a pain. It was like, 2-3 pages of algebra, which is, inconvenient. But here's the alternative method. Note from this given information, having as we do the Jordan basis. You can read the Jordan basis straight off of that arithmetic. Knowing as we do the Jordan basis, knowing as we do that the matrix exponential times the Jordan basis will always give us the fundamental set of solutions. Right? This is always do this, right? Matrix exponential times Jordan basis vectors always works. All we have to do is evaluate with that formula. 3 different times, of course. Right? And we went through the details last time. Let me do the last one again. This is the most interesting one. E to the xa times W3. This being W3. Sorry. That's a 3. So that's a 3. That's a 2. That's a 1. All the rest of this disappears. So we're back to the beginning, as it were. And notice that that is exactly that. Everybody okay? Now again, I'm not proving this formula, right? You can just take it as given, this formula up at the top. What we're learning here is just observing how to apply that formula. Yeah. How to get the coefficients in, where the 1 and a half come from. So that's one of these things that you're not really responsible for. I'll give you a very broad answer to that question, and that is, if you go back to this formula that you're not responsible for, there they are, 1, a half, etc. Now, where in this formula, roughly speaking, did they come from? Roughly speaking, they come from the definition in the first place of a matrix exponential. And you can see those coefficients, 1, a half, etc. So really all we're doing is, in these several formulas that I'm telling you you're not responsible for, we're taking this one definition and we're just kind of playing with it in different clever ways.
So the coefficient is 1 over
factorial? Yep, it's always 1 over a factorial. Yep, that's right. Anybody else? Yes.
So if we were not given the Jordan basis, we would have to back solve?
Well, if you're not given the Jordan basis, then you can't do the back solve thing either, because that also requires it being that requires it being back solvable, right? So if you don't know the Jordan basis, all you've got then is this one trick that only applies for the 2x2 case. If you've got a 3x3 system and you don't know the Jordan basis, you've got a problem. Yeah, and that's keep in mind, all you guys are responsible for is methods that I'm showing you how to do in this course. The methods I'm showing you how to do in this course are not exhaustive, right? There are some cases that we're just not prepared to handle, so yeah. Again, reminder though, good news: MATLAB will always give you your Jordan basis and your Jordan formula. Yeah. Okay. Okay. Right. Okay, so that's where we left off last time, was with this example. And we applied the above formula. We got the fundamental set of solutions right here. Of course, this fundamental set of solutions doesn't have the actual Jordan basis vectors in them. W1, of course, you see there, and thus there, kind of there, and sort of there, right? W2, you see there, and thus here and kind of there, etc. Everybody good? Okay. Again, as I mentioned last time, notice that this fundamental set of solution that I've derived in just sort of a couple of lines of just, here's what the formula says, basically. Matrix exponentials on the Jordan basis always works. Here's how those evaluate from the given formula, and here's how it simplifies. I mean, just pretty much writing it down. This is as opposed to several pages of back solving and particular solutions and unfortunate coincidences and all of that stuff. Right? So this is a really nice tool. Yeah.
You asked for a general solution. We just multiply these out and add a C.
It'd be all linear combinations of these. So C1 times that plus C2 times this plus C3 times that. Again, if you want to multiply the exponentials into all of them, feel free. Yeah, I tend to give me the choice between something that's factored and something that's multiplied out. There's something kind of compact and organized about it being factored. So don't feel a compulsion to multiply this exponential factor into there. Yeah, totally. Anybody else? Yep.
If the last column of the Jordan vector or Jordan matrix was 0, 0, 4,
okay.
Then the last fundamental solution just e to the 4x w3.
Let me see. I understand your question. So you're talking about in the Jordan form here.
Yeah.
Okay, so you're getting to the very next thing I wanted to talk about. So this, I like to start with an easy special case. The special case that is applying here is that if you look at the structure of this Jordan form, there is exactly one eigenvalue block, but even more importantly, there is exactly one basic Jordan block inside of that exactly one eigenvalue block, right? So this is arguably a very, very simple Jordan form. And the way I have applied this formula hinges on it being that simple. So he asks the question, what do we do if, what if this was a 0? Right? And then our Jordan structure would be like this. And then how would it apply? Okay, so again, that's the very next thing I wanted to talk about, so thanks for the segue. And here's how that works. Something about this formula. And again, I haven't shown you where this formula comes from. Right? So something I did not yet mention about this formula is that if you look at these basis vectors, wi minus 1, you keep moving back. Okay, back to where? When do you stop? How do you know when you're done? And the answer is, you can almost kind of see it from the algebra down here that, again, you're not responsible for, so you don't have to look. You're welcome to look through this if you like. It's very readable. There's nothing really too mysterious about this. But the basis vectors in question, where you stop as you take these steps, one after the other backwards. You stop when you get back to the left side of a Jordan block. That's just how it works, how the algebra works out. So you identify the Jordan block. For any given Jordan block, that corresponds to certain columns. Those columns correspond to certain basis vectors. Remember, when you're talking about a, let's see here, let me zoom out one. When you're talking about a Jordan matrix, you're talking about with respect to a basis, right? So columns correspond to basis vectors. You look at just the basis vectors corresponding to one block at a time. So let me show you how that applies in my next example here. All right, so suppose that this is your Jordan form, like this. Notice that there's multiple blocks. Where the eigenvalue blocks are kind of doesn't matter, but here they are. What matters here is where the Jordan blocks are. Here's the first Jordan block. The first Jordan block corresponds to the first two columns. The first two columns correspond to the first two basis vectors. Okay. Next. The second Jordan block corresponds to columns 3 and 4, and thus basis vectors 3 and 4. Everybody on board? Again, don't worry about why this is. This is just what the formula turns out to be, and there's some tedium in deriving this. Okay, lastly, last block corresponds to column 5, and thus basis vector 5. So we're going to apply the above formula. We're going to do this. Right? We're going to, we have our exponential, our kind of Taylor-looking coefficients. We're going to go backwards one term at a time, backwards through the list of basis vectors until we get to the end corresponding to each block. So, specifically then, let's look at, let's see here, this, we'll start off with V1. What is matrix exponential times V1? Well, V1, conveniently, is an eigenvector. That's a column that doesn't have anything off the diagonal, and so this is an easy one. This is e to the 3x V1. And that's that. Right, that's the first one. Second one, e to the xa V2. V2 is the second vector of this little list, V1 comma V2, going up to this formula, starting with number 2. So that's a 2, that's a 1, and we stop. So we have just that. It's going to be V2 plus x V1. Like that. Everybody good? Now where things start to get different, now notice this is exactly what it kind of would have looked like if we hadn't paid attention to this point, but where it starts to get different is when we start looking at the next Jordan block. Let's look now at the blue one. Looking at this block. These are the basis vectors that we care about. Now V3 and V4, right? E to the xa times V3. Oh, conveniently, V3 corresponds to a column with only a diagonal entry. It's an eigenvector, simple formula for eigenvectors. This is just e to the, 4x now. 4 is the eigenvalue. Right? E to the 4x times V3. Right? And looking at the next one, e to the xa times V4. Let's go back to our formula. In this formula here, that's a 4, that's a 4, that's a 3, and we stop. There's nothing over there. We stop at 3 because that's what gets us to the end of that Jordan block. Right? V3 and V4 are the part of this Jordan basis that corresponds to that Jordan block. So when we get to the sort of start of that list, that big V3, we stop and notice this like that. You see we stopped at V3. How are we doing? Is everybody following the process there? You see, so this was a sort of a long answer to your question. Does that all make sense? Yeah, cool. Anybody else? Yes?
Can you explain why the third block is not grouped with the blue one again?
Say it one more time. Why the third block?
The yellow block is not grouped with the blue one.
Oh, yeah. So it's just about the rules of Jordan form. So Jordan canonical form requires that in any block, what you're going to call a basic Jordan block, there's got to be all ones just above the diagonal. So if I tried to group this as a large basic Jordan block, it just doesn't follow the rules, right? I've got a 0 there, and that just doesn't follow the rules. So the definition of Jordan form is that you have eigenvalue on the diagonal, and then ones immediately above the diagonal inside every basic Jordan block. So that just doesn't work. Yeah.
And going back to how the Jordan matrix was made,
yeah.
Who made the decision to put the one there?
Oh, this is a suppose you've got a differential equation, one of these systems of differential equations that you're looking at. Suppose this is what Jordan form ends up being. I'm just saying this is hypothetically, right? Suppose that you type in your matrix into MATLAB and this is what it spits out as the Jordan form, and so you take it from there. Yeah.
Okay, so the whole process that we're doing now doesn't necessarily have to do with the multiplicity of the eigenvalue. It has to do with the other group.
Yeah, that's right. The multiplicity of the eigenvalue only tells you about the eigenvalue block. It tells you how big the eigenvalue block is. And we need to look at something more sort of concealed than that. The multiplicity just doesn't tell you about how many eigenvectors, and worse, it doesn't tell you about what the structure, how many, what are the sizes and positions of the basic Jordan blocks inside of the eigenvalue block. Yeah, it's just harder to see. Yeah. Okay, great questions. Anybody else? Is everybody good? Okay, so some old exam questions. I thought I'd go ahead and walk you through some of these. Oh, by the way, so I sent an email out to everybody like an hour ago or something with some comments about what you are and are not responsible for in this section about Jordan bases and such. So specifically, there's some old course material from quite a few years ago at this point. I used to spend time talking about a method that in a significant number of cases, not generally, but in a significant number of cases would actually let you find analytically the Jordan basis. And it's a pretty cool method, and we just don't have time for it. Over the years, I've been making some tough choices about what I just don't have time for in this class, and that was one of the ideas that didn't make the cut. It's not in the book. It always was a supplemental thing, and I just kind of got to where I never had time for it, so I just axed it. So anyway, that being the case, I've axed it from the notes. You won't find it in the lecture notes, but I can't axe it from the historical record. Right, all my old midterms are still there, and that's what happened. And so I want it to be there as a historical record. But anyway, you should know that on those questions, there's several of them way back when, where there is this method that will look completely unfamiliar to you for finding a Jordan basis. You're not responsible for that. All right, did everybody get that email? So, now that said, that is one specific method for finding a Jordan basis, and you're not responsible for that one specific method. That does not mean that you're not responsible for finding any Jordan basis ever under any circumstances, right? And there are circumstances like this one where I do want you to be able to infer a Jordan basis. So, for example, if I give you a matrix written as a conjugation of a Jordan form, right, I want you to be able to infer from this that is a Jordan form, and furthermore, to be able to read from this what the Jordan basis is. And to, move along accordingly. Okay. Keep in mind as well, I don't want this to be the trivial matter of, you just always, it's always the one on the left, or it's always the one on the right, and just always take the columns and, brain off. That's just the formula. Just do it, right? I do want you to sort of be, heads up. I mean, think about, wait a second, should it be on the left or should it be on the right? Here, A is given as a conjugate of J. What if J was a conjugate of A? And which way does it go? So, do be aware that, I think it's important that you should, not only know what the right answer is there, but why. Right? And so the answers to those questions are right up Math 216's alley. So this is an example where I wanted to see who's heads up on that question. Right? So here's let's go ahead and walk through it then. So you can see here I've got A written as Q, J, Q inverse. That's J, right? And I'm calling this matrix here Q. So Q inverse JQ. Here, well, let's see. How do I? No, I better put the Q here. That makes more sense, doesn't it? Okay. So Q inverse JQ. Okay. Well, the thing is, notice that when we did our change of basis, let's go back to the notes. When we did let me go way back here to where it happened. Man. This thing here. Oops. Notice A was not Q inverse JQ. It's PJP inverse. So I set it up here with the inverse on the right, not on the left. Does that make sense to everybody? Right? So this question as phrased is a little misleading, as life will sometimes be. Right? So you have to look at this question as written like this and recognize and say, hey, this whole, having the inverse on the left, that's writing it backwards. What we need is to recognize this. Right? That this is, sure, there's an inverse, the matrix on either side of J are inverses of each other, but it's the one on the left that I actually care about. So P, namely Q inverse, is the one whose columns are the Jordan basis. Pretty good? Okay. Alternatively, if this whole business seems mysterious to you, feel very free to do as follows. You can totally just take, as written like this, A equals Q inverse JQ, and just do the attempted decoupling again on your own. So if you have Y prime equals A Y, then just rewrite this as Y prime equals Q inverse JQ Y. Move this to the other side. You get QY prime equals J QY. And notice that your motivation here then is to refer to QY as Z. And thus, the Y that you're looking for. In other words, after you take your Jordan form and do the whole, back solving to decouple your system, et cetera, it remains that you're going to have to take those Z solutions and multiply by Q inverse. Right? So you don't have to call it P and set it up this way. You can leave it in this form, but unavoidably, you're still going to have to invert that matrix to get the one that actually that you use to recover, from your Z's to recover the actual Y's you're interested in. Does everybody see how that works? This is just a sort of an alternative point of view, in case you might prefer sort of morally equivalent point of view on it. Okay. All right. So that being the case, we've got to find this matrix, this Q inverse that I multiply by Z. So there's that row reduction, and here it is, and there's my Jordan basis, and everything from here is kind of plugging into the formula, and you see the V1, V2, and V3 showing up down here. Everybody on board? By the way, note the relevance of the Jordan blocks in this. Going back up to here, you can see our Jordan block. We start off with a 1-by-1 Jordan block, eigenvector, easy formula, and then we have a 2-by-2 Jordan block that's relevant to the basis vectors V2 and V3 only. V1 was part of the first Jordan block, right? That's V1. We're done with V1. There's no more V1s. Evaluating the matrix exponentials on V2 and V3, you stop when you get back to V2. Yeah. Everybody good? Okay. All right. So that was a little devious, but again, that's what I want you guys to be heads up, prepared for is, anticipating, having to figure out for yourself which one is the one that you actually care about. Okay, similar thing here. Want to solve y prime equals ay. There's the matrix A, and then I've given you, I've effectively given you the attempted, the failed diagonalization, right? I've given you the Jordanization here. I've just given you the Jordanization in a way that it's not immediately clear which one is which. I didn't give anything a name, either helpfully or unhelpfully. Right? So you've really got to, from first principles, figure out for yourself. Now, wait a second. Okay, that matrix is that matrix. Okay, so this is the A. Clearly, these matrices are inverses of each other, so this equation is a conjugation of this Jordan form. So this is the Jordan form for that A, but which one of these, is that my P or is that my P? Which one is it? Right? Okay. So again, different ways to think about this. I like to very often interpret that when you have a conjugation, right, every conjugation can be thought of as a change of basis. And just write it explicitly in change of basis language. A is in the language of the standard basis. J, the whole point of J, is that it is in the language of my new basis, my Jordan basis. Right? And that means, now just looking at this equation down here, you can unavoidably see that this is from S to V, this is from V to S. We know it's the one that's from V to S, whose columns form the Jordan basis. So therefore, that's the one whose columns are the Jordan basis. Yep, in the back.
Which exam is this?
I'm sorry?
Which exam is this?
Oh, I believe this was from the most recent spring, if I remember correctly. I'm pretty sure. Yeah. In fact, let me just check. I'm morally sure that's right. Yeah, this is from last spring. Yep. Yep. Okay, so at this point, again, it's all over, but the plugging in at this point, we're just going to plug into that usual. Look for our Jordan form. Notice that our Jordan form has a 1x1 block there, and then a 2x2 block there, and following the usual rules for the 1x1 block at the beginning, we get that being V1. And for this 2x2 block involving vectors V2 and V3, therefore, we get these formulas involving V2 and V3. And it's just a bunch of plugging in. Yeah. Everybody okay? Okay. All right. Okay, let's see here. So let me go back to the notes. Wow, we are short on time. Okay, so I want to do just a couple of quick things before we call it a day. Yeah, so we're moving on now to non-homogeneous equations. Keep in mind that big picture, our strategy here is we're trying to solve, general linear first order systems, and we talked about how to find homogeneous solutions. That was cases, right? There was the diagonalizable case, the non-diagonalizable case. That was all homogeneous. Now we've got to figure out how to find particular solutions, and then, as always, particular plus homogeneous gives the general solution, right? So we're on to the sort of the second part of that problem. How do you find these particular solutions? I'm going to show you two different ways to do it. The first way to do it, I'm not going to show you the proof. The proof is here in the notes, and you're welcome to read it if you'd like. But it's it involves some work that's kind of analogous to stuff you're going to do in Math 353 anyway. And furthermore, proof is not the focus of Math 216, so I don't feel like we're under an obligation to do this proof anyway. So I'm just going to cut to the punchline. And here's the nice punchline. If you have, let's go back to the if you have this equation with a non-homogeneous term here, G, then this, well, I'll just do it like this. This formula here, plug your G into this formula, and out comes a perfectly acceptable particular solution. And it's really nice, really convenient. By the way, notice the use of this matrix M. M is the fundamental solution matrix to the original homogeneous system. It's the same M that we've previously talked about. Okay, so let me show you some quick examples of what that looks like. It's just a bunch of algebra, and we won't have time to get through a significant amount of that here. But suppose you want to find a particular solution to that system. Here's your non-homogeneous term over here. Right? Where does that particular solution come from? Well, first, look at the homogeneous part. We've already talked about how to find homogeneous solutions. Again, you'll recognize the same matrix of constants that I keep pulling back over and over again because it's just arithmetic. Why not reuse that convenient arithmetic? So that matrix, remember, it's got certain known eigenvectors, eigenvalues likewise, and here you go. Here's your fundamental solution matrix. Right? You've seen these solutions before. So that matrix is what goes in here. And plug and chug. It is a multi-step process. This is tedious, but it works. First, you've got to invert that matrix. Then you've got to multiply by your non-homogeneous term, your G vector. Then you've got to take an antiderivative of that vector-valued function, which can be annoying. Y'all all remember Calc 2. And then you've got to multiply, when you're done, that antiderivative vector times m. So tedious algebra. So here's the, I'm going to kind of skip over the details. There's how you invert the matrix. We got lucky. Here it was 2 by 2. 2 by 2 matrices are easy to invert. By the way, make sure you remember that formula. It's super, super handy. How to invert a 2 by 2 matrix, right? Big win. Multiply that times G. Hang on. So M inverse times G multiply that out, and you get this. Next step in the formula: take an antiderivative of that. Right, and this is where it starts to get really ugly. Y'all all remember, I'm sure, when you take an antiderivative of one of these things, integration by parts. And now, integration by parts is not the worst thing in the world, but it is, kind of a multi-step process, and you might want to, work that out on the side somewhere to kind of not interrupt the flow of your calculation. Be real careful with the minus signs. Of course, there's, notorious, dangers of minus sign errors with integration by parts. Here's that antiderivative. And again, you're still not done. Then you have to multiply that antiderivative, multiply that times the original M matrix, and there's your final solution. So anyway, it's just a process. And next time, next time we have an exam, but on Friday I will show you a different way to solve these kinds of, to find these particular solutions. All right, see y'all later. Have a good one.